Okay, welcome everyone. My name is Sophia Mohammed and I am chair of the Greater Houston section. And today it is our honor to have Dr. Mary Carroll, the 2024 ACS president, who will give a talk on aerogel materials. And so very quickly, Mary Carroll is the Dwayne W. Crichton Professor of Chemistry at Union College in New York and the 2024 president of the American Chemical Society. Mary earned a bachelor's in chemistry from Union College, a PhD in analytical chemistry from Indiana University, and performed postdoctoral research at the University of Massachusetts. At Union College, she teaches courses in introductory and analytical chemistry and mentors undergraduate research students. She co-directs the Union College Aerogel Lab, a vibrant and productive interdisciplinary research group. In addition to the fundamental studies, the group investigates applications of aerogels in sustainable buildings, chemical sensing, drag reduction, and automotive pollution mitigation. Mary co-founded SunThru LLC to commercialize the aerogel technology developed at Union. Mary has been a member of ACS since 1986 and an ACS volunteer leader since 1993. She served as a counselor of the Eastern New York ACS section from 1998 to 2022. Representing the section at council meetings and participating in the Eastern New York Executive Committee meetings. At the national level, she has served on the ACS Committee on Science, the ACS Leadership Advisory Board, and served and held leadership positions on the ACS Council Policy Committee and the ACS Society Committee on Education, the ACS Women Chemists Committee, and numerous working groups and task forces. Based on her contributions to science and service to the ACS, she was selected for recognition as a member of the class of 2016 ACS Fellows. And without further ado, I will hand over to Dr. Mary Carroll.
Well, thank you very much for the invitation to be here and for the nice introduction. I'm going to share my screen and then I'm going to start the PowerPoint, I think. All right, so can people see the screen?
We can see the screen.
Excellent. I am going to minimize on my end what I'm seeing. And can you see the whole screen, or that's really up to you? Is that right?
We can see the whole screen and the view is up to the person.
Okay, perfect. So I'm going to talk a little bit about aerogel materials, and I deflected the question about how'd you get into aerogel materials from the social time, because I was going to describe it here. But I'm going to talk about the journey from research to commercialization, but also the journey, how did I get involved with aerogel materials? So there we go. So just a little bit of background on what are aerogels. So they're nanoporous, low-density materials. They're generally network solids, but they're made in such a way that they have extraordinarily low density. So there've been a couple of Guinness World Records on aerogels in the solid, being the lightest density solid. They're shown on here. The most recent one that I'm aware of are carbon aerogels made with carbon nanotubes and graphene sheets that have extraordinarily low density. Aerogels have interesting properties because of this. They have very high surface areas. And some of them, the silica aerogels, are extremely highly insulating. They're relatively strong. This picture here, if you can see my cursor, there's a silica aerogel under a brick. In compression, silica aerogels can hold up something like 1,000 to 10,000 times their mass, but they don't actually weigh very much. And again, they have really low density. They can have high insulation. This little cartoon here shows the typical structure of some silica aerogels. They're formed from colloidal mixtures. So you have colloidal nanoparticles that then link together. So this isn't meant to be an atomic level structure, but it's to show a colloid. They're considered nanomaterials because they're nanoporous. They have pores on the order of nanometers to tens of nanometers in size. And what this means is they end up with a pretty high surface area to mass ratio. And so that's really attractive for applications in things like sensing and catalysis. And that's, in a way, how we got into that. Now, there are commercial applications, and there have been a lot of applications of aerogels that you may be familiar with. So you can purchase very highly insulating materials that have like coats and blankets. And one of my sisters has a pair of slippers, household slippers that have aerogels impregnated into the material to use as insulators. We've done some work in aerogel-related windows. NASA and other space agencies, including the European Space Agency, have used aerogels on a number of different things for insulators, including the Mars Pathfinder rover. They've also been used for some of their structural properties. And another big NASA project is shown in the bottom of this slide. This was the Stardust project. Monolithic, so single-piece silica aerogels in big arrays were used to collect particles from comet dust. And this on the right lower part shows comet dust particles tracking into the aerogel. Because they're so porous, the particles could get trapped in the material, and instead of being burned up on the surface, they could in fact be captured without necessarily fully thermally decomposing. They brought these big arrays back down to the earth, and then they used citizen science to try to identify where there were these particles. You could be trained on a computer to look for particles. And in fact, my collaborator at Union College found a particle, and then she got naming rights for the particle. We started working on aerogel research at Union actually because a student that had worked with my long-term collaborator at the time, just one of my friends on campus, Ann Anderson, a mechanical engineering professor who was working with heat transfer and fluid mechanics and liquid crystal thermometry, had a student who had done a project with her bring her this picture. This is one of a pretty famous series of pictures that NASA took. Again, it was affiliated with the Stardust project, but just showing some of the properties. And so you may have seen one of these before, a silica aerogel, and then there's something on top of it, in this case, a flower, but sometimes it's Hershey's Kisses or a crayon, something that would normally melt. And then you have some sort of torch or Bunsen burner underneath it. And at least in the time frame when the picture is taken, the object on top is being protected by the insulation. And so this student, Ben, said, I want to make an aerogel for my senior project. And sort of the short version is that Anne said, well, that's great, but we're going to have to talk to some chemists. And so she sent Ben to me because she knew that I was working with some materials. And again, as Sophia described in the introduction, my prior expertise was in analytical chemistry. I was designing instrumentation for molecular spectroscopy using lasers and fiber optics. I was doing chemical sensor work and also doing some fundamental studies of dye interactions in solution and sol gels. And when Ben came to me, I said, well, I know what aerogels are, and aerogels are really cool. I've been working with sol gel materials, and aerogels are a type of sol gel material, but I haven't been working with aerogels. I said, and we don't have the equipment to make them. And I was particularly interested in it, though, because I had very recently, before Ben had come in, I had read this paper. Nick Leventis, who's now at Aspen Aerogel, but at the time was at the University of Missouri-Rolla. Sorry, I went back too fast. And then Deborah Rollison at the Naval Research Laboratory had collaborated on this, and they had made a sensor that could sense oxygen near the speed of open air diffusion by tethering it to the silica backbone of a silica aerogel monolith. So I'd read this, it was really cool. I said, this would be really cool to work with. I'm already working with these, but we simply don't have the equipment on campus to make it. And so I'm going to take a little detour into chemistry. Even an analytical chemist can do this as synthetic chemistry. My previous work did not involve synthetic chemistry at all, but it's actually and I had started doing some sol gel work. If we think of silica aerogels, we often start with a silicon alkoxide. At the top, we've got tetramethyl orthosilicate. At the bottom, we could do tetraethyl orthosilicate. We have these methoxy or ethoxy groups or other groups like that. If you hydrolyze this to make some hydroxyl groups splitting out an alcohol, you can then start to link these together. So these silica precursors are liquids. If you can mix them with water, which they're not actually miscible with, and so you put in a solvent like methanol or ethanol with them, If you can get the hydrolysis reaction to occur, you can then do a series of condensation reactions where you link together either the hydroxyl group with another methoxy, and you ultimately make this silica network, a wet gel that's pores are filled with alcohol water mixture. And you can do this with a variety of different precursors. You can change the functionality by having, instead of 4 groups, you can have a group that's not capable of going into these condensation reactions. But it's relatively easy chemistry to do. And again, we could have 2 hydroxyls react, we split out water. So you could end up with an alcohol water mixture, and you have a gel that's a wet gel that has this very, this network that goes through the whole space, but the pores are filled with liquid. And so this is pretty easy. The difficult part is taking the wet gel all the way to an aerogel, removing the solvent and leaving the pores filled with air without causing the pores to collapse. And so if we just start with a typical silica gel filled with solvent and we let the solvent evaporate out, as the solvent evaporates out due to capillary action and surface tension, the pores start to collapse. And as the pores collapse in, you end up with a material that is still porous. It's a zero gel, where zero is a Greek prefix meaning dry. And these are porous materials. These are the sorts of materials I was working with for chemical sensors. I was entrapping fluorescent probes in these materials. But aerogels are more porous. They have higher surface area. It's just a little bit nicer properties to work with and a little bit more extraordinary properties. And so the issue is that there are 3 general approaches to fabricating aerogels, and all of them try to avoid this crossing this line from the liquid to the gas phase. And because I took this from my colleague in mechanical engineering, they tend to call gases vapors, so it says vapor here. But this is just a phase diagram, a generic phase diagram. Here's our supercritical point. So if we have this material, I'm starting with the star, we've made the gel. We want to keep the solid, but we want to get the liquid out of the gel. There's a couple of different choices. One choice is to cool this down, drop the pressure, and sublimate the solvent out. And that's a freeze drying approach. And it's relatively straightforward to do, but it typically results in powdered materials, powdered aerogel materials. Another approach is to surface modify the matrix, in this case, a silica matrix, surface modify the matrix so that surface tension is reduced considerably, and then you might be able to dry it under ambient pressure conditions, allowing the solvent to evaporate in somewhat controlled, you might be changing the temperature slightly in controlled conditions. If you do this very carefully and very slowly, you can end up with monolithic single pieces of aerogel. But it takes a fair amount of time and frankly takes a lot more chemistry than I was hoping that we would do. The most common way to make aerogels is supercritical drying. And the most common way to do that is by using a pressure vessel. It's essentially an autoclave, a critical point dryer. You have to get the liquid into the supercritical phase. So you have to either get up to fairly high temperatures and pressures, or you have to pick a liquid that doesn't have as high temperature or pressure critical point. So the more conventional way this is done would be to do a series of solvent exchanges with the wet gel, replacing that alcohol water mixture with a more non-polar solvent, maybe acetone or hexane, through a series of exchanges, and then putting that into a critical point dryer and filling the critical point dryer with liquid CO2 and doing a series of CO2 liquid exchanges before taking CO2 supercritical, which can be done at reasonably high pressure, but at temperatures a little bit below 40 degrees C. And the critical point dryer is the method that I was very familiar with, and we did not have a critical point dryer. And so that I said, we don't have the equipment. We could try to think of a way of doing this, of getting above this critical point, but we don't have the equipment on campus that I'm aware of to do this. And I want to say a little bit about the campus where I teach. So I teach at Union College in Schenectady, New York. We're in upstate New York, near Albany, near the capital. We're strictly a bachelor's degree granting institution. So we technically are a predominantly undergraduate institution, but we really have no graduate students. So we're an undergraduate institution. We have courses of study in the liberal arts, including the sciences. What's a little unusual about Union is we also do have engineering. We're a private institution with about a 10-to-1 student to faculty ratio. So, and an expectation that faculty are going to engage in high quality research that's exposed to peer review. But we are working strictly with undergraduate students. So we have pretty good facilities, but we didn't have everything. So we didn't have that. So since we didn't have a critical point dryer available, we sent the student to literature and we started working with the students. And we came up upon some different papers coming out of Lawrence Livermore National Laboratory in California on rapid supercritical extraction. We'd seen this particular paper, rapid supercritical extraction process for production of silica aerogels. And what they were doing was making the wet gel in a contained mold held within a pressure vessel. And they were actually taking the liquid that was in the pores of the mold, so this alcohol water mixture, more alcohol than water. They were taking it up to the temperatures and pressures needed to release it as a supercritical fluid. And so then they had various valves and pressure relief valves and things like that, because it's a high temperature, somewhat under 300 degrees C, high pressure process. And so we also didn't have this equipment. But what we did have was mechanical engineers, and mechanical engineers do study materials and they study the strength of the materials. And one of the ways that they do that is by breaking the materials, right? So they had different equipment used to do compression tests and tension tests, and they had a hydraulic hot press. And so over the course of the next about year and a half, working with undergraduate students, we actually invented a different way of making aerogels. And it employs a hydraulic hot press in a confined metal mold. We patented and published work on this, and this is really what started us on what's now been more than a 20-year journey working with aerogel materials, because when you develop a new method for something, now you have all sorts of interesting things to study. How does your method work? How do the materials you make compare to the materials people make with other methods, and so on. So I'm going to take you through the method just a little bit, but it uses a hydraulic hot press in a confined metal mold. So this is just a photograph of a hot press. It's got two platens. Hot presses are used to do things like laminate, right? Materials and other things like that. So they're not really designed to make aerogels. The way it works is that we can pour our liquid precursor mixture into the well of a mold, seal it close the platens around it, and then because it's a hot press, drive the temperature of the metal platens up. That increases the temperature of this metal mold, which increases the temperature of the materials that are in the mold. During the initial part of this process, the gel forms, and then we take the temperature up higher. As the temperature increases, and now we have this is pressure versus temperature. This is the methanol liquidus line, the line between the liquid and the gas, and the red and then gray and blue line is our process. So this is actual data. As we take the temperature up, it increases the pressure within the mold. And we did this by using an instrumented mold. And we can get the temperature and pressure conditions above the supercritical point. What we then do, once we're sure we're above the point, we then release the restraining force from the platens, which allows the liquid to escape as a supercritical fluid. And then we cool the mold down. And we can make monolithic aerogels in 3 to 8 hours. So if you think of this as analogous to cooking, you have your prep time of mixing the stuff together, you put it in the mold, and a few hours later you have aerogels. We had to spend some time getting the parameters right. But this has made it a process that really facilitates doing research with undergraduate students, because undergraduate students do not, other than maybe a few weeks in the summer, they don't work full-time on research. And so the traditional methods of making aerogels, where you have to do a whole series of solvent exchanges and then put it in the autoclave and do more solvent exchanges, a typical process with the critical point dryer takes days to do instead of hours. And so we started making aerogels we started this collaboration in 2001, 2002 academic year. By 2003, we were making monolithic silica aerogels. This is an example here. Here I am in the back, and my collaborator, Anne. This is now just over 20 years ago, with some of the first students that were in our group. This is after the first student, Ben, graduated, but I'll just point out a couple of people in here. This is Smitesh Bakrania. He's now tenured faculty at Rowan University in New Jersey. Next to him in the black tank top is Becky Wolf-Stiles. She's head of product sustainability for BASF for Europe and Asia. In the blue vest here, this is Professor Desiree Plata of MIT. She was an undergraduate student with us, and she's in the civil and environmental engineering department at MIT now. So we've had some really, again, the other people in this picture also have done very interesting things. We have very strong students, but we don't have them for very long. We were able to make these aerogels. We're making silica aerogels with very little shrinkage. And in fact, the first few papers we published, we explained that it's actually very difficult for us to get these aerogels out of the mold without breaking them, because they fill the entire mold. And the reviewers did not believe us. So we would constantly go back and forth on this. And we eventually published a paper in the Journal of Visualized Experiments, video protocol, and nobody's been asking us about that since then. But so they make very nice aerogels. They're not the best aerogels that anybody's ever made, but they have very good properties. And as a result, having designed this new method, it's led to a number of fundamental studies. How does our rapid supercritical extraction process actually work? What, fundamentally is going on at the different stages? And we've done fundamental work on understanding gas flow through aerogels, investigating structural changes that can occur. But we've also done a lot of applied work. A lot of our most recent work has been either in catalytic aerogels, which are typically the ones we've been working with have been mostly alumina-based. I'm not going to talk about them in detail here, and also silica aerogels. And silica aerogels is where we moved into commercialization. So I'm going to tell a little bit of a story about the windows for sustainable buildings. But we've also done work with silica aerogels for drag reduction with hydrophobic aerogels. A lot of our initial work was in gas sensors, because that was the research area I was interested in the most at the time, was the sensor work and other sorts of applications. And so we just have a few things. I want to point out this picture where you see that somebody with a lab glove holding, this is a roughly 5 by 5 inch silica aerogel, and it has extremely high translucency. So we were involved, we were working with students, we were doing lots of interesting projects, and we started to get a fair amount of funding from the National Science Foundation. I'm going to flip back to the previous slide. We've had funding for equipment, we had funding for work with sensors, we had funding for tailored aerogel work, so investigating structural changes, can we tailor the material for different applications? And when you have funding from the US National Science Foundation, you get a lot of email about other kinds of National Science Foundation funding. And one thing that we kept getting notices about was the NSF Innovation Corps. It's also called I-Corps, which is designed to translate technologies from the lab into the marketplace, because NSF funds a lot of fundamental research, but it funds it with taxpayer money. And so they'd like to see eventually it go into commercialization. Many of you may be aware that the National Science Foundation, just within the last year or so, established a new directorate. There hadn't been another technical directorate at the NSF in a couple of decades, but now there's a Technology, Innovation, and Partnership, TIP, directorate. And NSF Innovation Corps, which has been around longer than that, is folded into the TIP. And the mission is to do this. It's a short, the NSFI course, I think a $50,000 grant. It's an intensive program to explore tech transfer, and it culminates in a go, no-go decision. So we had seen a number of these emails, and Anne, my collaborator, had a sabbatical coming up, and she said, maybe this would be an interesting sabbatical project. We also had a student working in our group who had transferred into Union. He was a little bit off sequence, and he was going to be finishing his coursework at the end of the fall term, but wasn't going to start grad school till the following fall. And so the I-Corps program, you have a entrepreneurial lead, which is typically a grad student or a postdoc, but we don't have grad students or postdocs. There's the PI, which was Anne in this case, and you have to have an entrepreneurial mentor. And so we knew we had somebody that could be the PI and the entrepreneurial lead, and we didn't know how to find a mentor. So we asked the National Science Foundation, program officer, so if we're going to apply for this, how do we go about finding the entrepreneurial mentor that we need? And they said, you just go to your tech transfer office and they'll assign you somebody. Well, we're a liberal arts college. We do not have a tech transfer office, okay? And so in a longer email, we said, we don't, we were asking some other questions, and we don't have a tech transfer office. And we got the response back, you've got to go to your tech transfer office. So we sent another message saying, we do not have a tech transfer office. And then they caught on, and they said, we'll try to give this some thought. And in the meantime, Anne found someone that she knew that had retired from General Electric in the area, and that was interested in taking this on as an interesting project to do. A difficult thing with the NSFI core program is that the only person that really gets paid is the entrepreneurial lead. So if you have a tech transfer office, somebody's paying them to do the work, and the faculty members already getting paid. So that's not a problem, but we had to find somebody that was willing to volunteer to be the lead. They interviewed 72 potential customers. The only team from a PUI to participate in that particular cohort. And I think at that point, we were either the first or second team from a PUI in the NSFI core program, totally. But the outcome was, we discovered there was a potential market for these monolithic windows, right? For monolithic aerogel windows in daylighting. And as many of you know, US building sector accounts for a huge amount of electricity use within the US and other countries as well, and also associated greenhouse gas emissions. And that the major areas of energy consumptions are heating and ventilation and air conditioning. A substantial amount of energy loss in buildings, whether that's keeping the heat in or keeping the heat out and keeping the air conditioning in, an awful lot of it goes through windows. Windows tend to be lossy in terms of that. Now, one option is to simply make rooms without windows, but those are not terribly attractive rooms to use, right? And there are certainly health benefits from having natural light, productivity benefits. You don't really want to have buildings without windows, and yet windows cause us to use much more energy than we need to. And so the idea was, if you could use aerogel materials that have these insulating properties, and we're certainly not the only ones to think of this, that there are lots of different applications where you might be able to use them. And I'm showing some figures from the new Springer Handbook of Aerogels, which just came out last year, and from the chapter about aerogels for super insulation. And a lot of this work is being done in Europe, but not exclusively. So daylighting, a couple of these are examples of daylighting. So bringing light in, but not necessarily a transparent vision window like you'd have in a home, but light, you could bring daylight into atriums, and gymnasiums, things like that, where you're bringing some natural light in. And the lower two pictures are showing that, but they can also be used in bricks. You can put aerogels in bricks to have highly insulating bricks that do not weigh as much. They can be used in plasters for walls or in flooring. And they can also be used in windows. Now, there are major aerogel suppliers in the US. One of the biggest is Cabot, which sells granular aerogel products. And so you could fill the space between a double pane window, for example, with granular aerogels and bring diffuse light into a building. And they have a number of products with that. Aspen Aerogels, which I've also mentioned previously, they also have products that have high insulating. And there are other companies, including Aerogel Technologies, which has licensed some of NASA's technology for polyimide aerogels. Now, these are clearly not transparent, so this would not be appropriate for a window, but is appropriate for other insulating areas. And so we established a company, a startup company, about 10 years ago called SunThru LLC, and we went after NSF funding, and our company got an NSF STTR, which is Tech Transfer Phase 1 grant, with a subaward to Union. So we were doing a lot of the research work at Union, moving toward making larger aerogels and larger monolithic aerogels that had good properties. We subsequently, the company got funding from the New York State Energy Research Development Authority, and tried for the phase 2 unsuccessfully. The reviewers in that case were completely correct that we were not yet ready to move toward manufacturing. Anne and I, of course, are doing this as a side project, but we had a couple former students come to us and say, you know, we're really interested in coming back to doing aerogels, and we'd like to do something more with the company. And so they joined in, I think, about January 2020. And by August, they had landed another phase 1 grant to do some work for aerogel applications. They entered some pitch competitions and commercialization competitions. We got some more NYSERDA funding. And so the company currently has an SBIR, so small business transfer related phase 2 thing. This is now separate from Union. The company is now scaling up for manufacturing using this NSF money, as well as money from the New York State Energy Research and Development Authority, and has rented space nearby, is building equipment, and we have some full-time employees, most of which were former students from our aerogel lab. And so what started as sort of this is kind of an interesting sabbatical project, turned into establishing a company that is now working toward making things. And I'll talk a little bit about some of the work that we've done. On the first grant, we scaled up. We thought we could make bigger pieces. These are the size that we can achieve with our laboratory scale hot presses, but hot presses come in much bigger sizes. And it just shows thermal performance. I'm going to show you, this is just aerogels. A basic double pane window, the U value gives you an idea of how well it's insulating. A basic double pane window would be about here at 2. If you put aerogel inserts in between the 2 panes, it drops it by a factor of 2. And if you pull a vacuum on that, it goes down even farther. And so we started thinking about this for daylighting applications. You can see this is a small window with 4 tiled pieces, and you can see there's pretty good translucency. So we started thinking more about, could we start doing it in a more window application? Some of the work we'd published was with the small pieces. We started to see other people's work in the literature, and this is work we've done now in collaboration with Professor Cenzia Barati at the University of Perugia in Italy. These are not the most attractive windows. These are made by tiling pieces together. But if we tile big enough pieces together at Perugia, they can put them into equipment where they put it in a window location, compare it to other window functions. And these are large enough to do some of these tests with in simulated rooms where you have heat outside and air conditioning inside, or vice versa. We have looked at how can we improve the transparency, and one obvious way is simply by decreasing the path length, but another way is by changing chemical recipes. So we've done lots of different work. Some of this was published relatively recently. And this is an example of one of our thin aerogels. It's in between two panes of glass. And you can see that the optical transparency is excellent. This is greater than 90% optical transparency through the visible. And so the company is now working on expanding these to more actual window size pieces. And that's what our current grants are doing. We've also done some work in taking aesthetic approaches toward windows because, for example, nobody expects that they're going to have perfect vision through a stained glass or mosaic style window. And so we've gone back to putting some dyes into aerogels. I used to do it to make sensors, and now we've been doing it to make aesthetically pleasing aerogels. We've discovered when working with the aerogel artist, Professor Yanis Michalotis, he works in Cyprus, he's from Greece, that we can actually use laser cutters to etch designs on aerogels. And we can also improve translucency by heat treating. It's not obvious in this picture, but there is an aerogel in front of that representation of the Knott Memorial. And again, here is the Knott Memorial from campus. There are lots of startup companies. And again, this is a section on the aerogel industry from the new book, Springer Handbook of Aerogels. Our startup company, SunThru, is not the only one that's working in the space of translucent aerogels. There's another one called Aeroshield, which is a spinoff out of MIT in the Boston, Massachusetts area. TM Factory in Japan is doing it. And I'm just highlighting these, not just because they're essentially our competition, but also because each of these companies is using a different method to make aerogels. And so it's a nice way to sort of wrap things up. If we go back to the different drying methods that we have for making aerogels, again, we can mix precursors. And what we're doing is mixing precursors, pouring them in the mold and doing rapid supercritical extraction. So this is SunThru's approach. But you can also mix the precursors, let gelation and aging occur and do freeze drying, or solvent exchanges, and then going to CO2. And what Aeroshield is doing is this. They're doing the CO2 and they're simply using larger and larger critical point dryers. And so they're a little bit ahead of us in terms of size. They're able to make something like 12 or 14 inches by 20-inch gels in large autoclaves currently. And the process that TM Factory is using is the chemical modification that allows ambient drying. And they're able to make very large monoliths, but it literally takes months for the entire process, including the drying, to occur. And so we're all working toward, could we put aerogels in into a window process? And it's interesting to see that each of the groups is taking a different approach. This picture actually was taken today on the Union College campus because we had group meeting, and these three in the center are actually visiting Italian students from our collaborators lab at the University of Perugia. The 5 students at the left are Union College undergraduates. There's another Union College undergraduate second from the right, and a high school student that works in the lab from the local area, from a rural high school there. But one of the ways I ended up working with aerogels is that they're just really motivating materials to work with. They have such extraordinary properties that they lend themselves to a lot of interesting applications. And a lot of these have to do with sustainability, our sustainable building work with the windows, the automotive pollution mitigation, the potential for using aerogel catalysts to replace platinum, rhodium, and palladium, so precious metals that are used currently. These are engaging and motivating for both the students and for the faculty members. So it's just been a lot of fun to work in a collaborative group where we've got scientists, we've got engineers, we have to learn how to talk to each other. We have to learn that sometimes the words we use aren't the same, or sometimes when we say high temperature and somebody else says high temperature, they're really talking about different temperatures. Or my favorite example, when we were first working with the students and we were doing the sensor work and I was talking about probes, I meant fluorescent molecules. And when I was saying probes, all of the engineers in the room were thinking about a device. And they did not understand what I was talking about until somebody finally asked the question. And we realized that we were talking on entirely different scales, but we were using the same words. We have established an aerogel laboratory, mostly because of a significant amount of funding from the National Science Foundation to purchase equipment, but also to build equipment. And the bottom right here is actually a catalytic test bed we built with a National Science Foundation major research instrumentation grant to build instrumentation. And these are, a variety of students doing a variety of things in the lab. We've been fortunate to be able to collaborate with people within the U.S. and outside. Our work with catalytic aerogels is with a colleague at Union, Professor Brad Bruno in mechanical engineering. I've mentioned Chenzi Barati and her group, and the artist, Professor McLudis, and then SunThru with a number of our former students. We've had substantial funding from the National Science Foundation, from the college itself, from New York State. And both Anne and I are currently on the Fulbright Specialist Program, and that gives us the opportunity to potentially go for chemical and mechanical engineering education-related transfers. Much of the research I presented today was funded by the U.S. National Science Foundation and NYSERDA, as well as Union College, and I've got the grants there. I mentioned that we were one of the first groups from an undergraduate institution to get involved in some of these technology grants from the National Science Foundation, and we were encouraged by our program officer for one of these grants to consider putting in for a workshop. So we're running a series of workshops. The next one is this fall on the Union College campus on technology, innovation, and partnership activities, helping build a community of practice among PUI faculty members and encouraging people to think about how they could move their research from the lab to the marketplace, either for technology or for broader societal missions. And so we are currently accepting applications of teams of faculty members and administrators from PUIs. The NSF funding of this, it's again through the TIP Directorate, allows us to not only have this be free, but to actually have the housing and the transportation largely covered, possibly completely covered. The most recent round, we did one round online, one round last fall, and we had teams from as far away as Alaska. We had one team from Alaska and teams from across the US. So unfortunately, this is because it's National Science Foundation. It is limited to US institutions. I want to thank you and for the attention. I want to thank the Greater Houston local section leadership for organizing the event. And I think, probably talked long enough. I would be happy to entertain questions. And I'd also be happy to connect with anybody that's participating through social media. I'm on LinkedIn and X professionally. And I would be happy to answer questions. I think probably the easiest way to do this is to stop sharing the screen so that I can see people in the room. And then I'll go back to sharing the screen if somebody wants to see a slide. So thank you for your attention.